Forces 10, Interaction Forces. Lesson date, April 10, 2014 by Gurkha and Dhani, Bella Zhu, and Kimberly Tom.
High quality.
Go.
Hey guys, so today in this video, we'll be reviewing the Interaction Forces lesson for any of you guys who missed the lesson or want to review for tests or exams coming up. So, what exactly are interaction forces? Well, interaction forces occur when two objects, they interact with each other, and while they're interacting with each other, they produce the same force on each other. So let's get started, guys. In this lesson, we will be learning about the forces involved during collisions by examining 4 possible situations. So to get a better understanding of forces exerted by the car over here, the truck, or both, we'll be testing them out. So the large dynamic cart is this one, the truck, 500 grams, and this one is the small cart, about 250 grams. So, and for each situation, we will distinguish which force is present and compare their magnitudes. The force the truck exerts on the car will be written as Ft-C, and the force that the car exerts on the truck will be written as Fc-T. So, in situation 1, we have a truck pushes a stalled car from behind, and they move together at a constant velocity. So here we have the situation set up, and as you can see, they're both facing the same direction. So the car is stopped, okay, and now basically what's going to happen, the truck is going to hit it from behind and push it along the same constant velocity. So in the second situation, it says a fast moving car hits a truck at rest. So here's the car, there's the truck at rest, okay. So I'm going to put both the carts facing the same direction. The car is facing the truck and the truck is facing the car, okay, and this is what it looks like. Alright, in situation 3, we have a fast-moving truck hits a car at rest. So we're going to put both the carts facing the same direction. Truck facing that way, car facing that way. Okay, the car is stopped, okay, and the fast-moving truck hits the car, like this. In situation 4, the last one, we have a truck tows a car and they speed up together, and we have the cart set up facing the same direction, and we'll see here the truck towing the car just like this. After each situation, we concluded that each car produces a force on each other, the interaction force, which is the normal force. However, we don't know which force is bigger, and that's what we're going to find out. We're now going to take a closer look at the situation 3 where the fast truck hits the car and look at its velocity time graph. The red line on the velocity time graph represents the truck's velocity, the blue line represents the car's velocity. So now, in order to compare the interaction forces exerting on each cart, we need to first calculate the accelerations of both the carts by using one of the big 5 equations. Over here, we use the one final velocity equals initial velocity plus acceleration times delta t. And once we algebraically isolate that, we are left with acceleration equals the change in velocity, which is final velocity minus initial velocity, divided by delta t. Okay? And basically, now let's look at our vertical lines on our velocity time graph. These lines represent the starting and ending points of the collision. The first one represents the starting point collision. Second vertical line represents the ending point of the collision. Okay? Next, we decided to calculate the duration of the collision. So our delta t, so the time taken between the start and the end of the collision. And over here, we have our delta t calculated to 0.2 seconds. Next, we looked at t1. So at the first time interval the collision started, the velocity of the large cart is at 3 meters per second. And at the end of the collision, it changes to 1.3 meters per second. So therefore, when we calculate our average acceleration for the collision, we are left with negative 8.5 meters per second squared. And then we can use the same logic and do the same thing and calculate average acceleration for the smaller cart, which we get at 17 meters per second squared. So here we have our interaction diagram and our force diagrams for our collision in situation 3. So now our interaction diagram, we have 2 systems here, and we can easily see one is a large cart, one is a small cart. Those are our 2 systems, and we all know easy forces. We have a gravitational force with the earth providing that on the 2 carts. we have a normal force exerted by the track on the two carts, and then we have a normal force between the two carts on each other. And now this is represented in our force diagrams as two separate force diagrams, one for the large cart, one for the small cart. So let's do for the large cart. We have our force diagram. We all know we have our force of gravity acting on our large cart down. Okay, and it's represented over here with our force of gravity of the earth acting on our large cart. Then we have our normal force represented over here of the track acting on the large cart. And we can see that they're of equal magnitude. And then lastly, we have our normal force of the small cart acting on the large cart. Okay, and since we have our coordinate system showing up is positive and right is positive, we have our acceleration vector going in the same direction as our normal force, which shows a negative acceleration, which was shown on our velocity time graph as well. And now for a small cart, it follows the same format where we have normal force of the track on the small cart, force of gravity of the earth on the small cart, and they are the same magnitude. However, they are smaller than the one on the large cart because it has less mass. And now we can see that we have our normal force of the large cart acting on the small cart. However, it's in the opposite direction, and therefore we have our acceleration squiggle in the same direction as our normal force, which makes the acceleration positive, which was also shown on the velocity time graph. So the next thing we have to do now is find the magnitude of each of the forces on each cart. And to do this, we would use Newton's second law, which is net force is equal to mass times acceleration. Okay, so now basically in the collision, there's only one important horizontal force acting on each cart, which was the interaction force between each other, the normal force. Okay, so now here we can see how our net force in the x direction is equal to the mass of the large cart times the acceleration of the large cart. So the mass of the large cart was 0.5 kilograms, and we calculated that our acceleration was negative 8.5 meters per second squared. And that is equal to negative 4.5 newtons as the net force, since it is going in the negative direction. And then for the net force of the small cart, we have net force is equal to mass of the small cart times acceleration of the small cart. And now the mass of the small cart is half of the large cart, so 0.25 kilograms, and the acceleration is double. It's 17 meters per second squared. And this results in 4.25 newtons as well. And we can see here that the magnitude of the net force are the same, however one is negative and one is positive. In conclusion, we saw that the interaction force between the two objects was the normal force which was exerted on each cart. Okay, and what we saw with those two the two forces was that they had the same magnitude. However, they were going in different directions. So one was positive and one was negative. So thank you guys for watching our video, and enjoy our drawings by Kimberly. That's me, that's Kimberly, and that's Bella.